Ladies and gentlemen, welcome to the Hong Kong IE Civil Division event, technical webinar on Depicting Photochemical Behaviour of Gaseous Secondary Pollutants, Environment-Specific Insights and Control Strategies from Near-Explicit Chemical Mechanism Modeling, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm the MC of today's webinar. We are honored to have Dr. Wang, who is a research assistant professor at the Department of Civil and Environmental Engineering in the Hong Kong Polytechnic University. Dr. Wang obtained his bachelor and master degree in applied chemistry from Sun Yat-sen University and got his PhD degree from PolyU in 2019. During 2020 to 22, he worked as a joint postdoctoral research fellow at Jinan University and PolyU. He has contributed to over 20 research projects and authored more than 30 publications with over 1,500 citations and an X-index of 21 as recorded on Google Scholar. Without further ado, I would like to invite Dr. Wang Yu to deliver the talk. Dr. Wang, please.
Okay, thanks, Fiona. Okay, good afternoon, everyone. I'm Wang Yu. Today, I will give you an online seminar about the ozone secondary pollutant chemistry. Okay, firstly, I will briefly introduce our department, CEE, and first is global recognition. And we have many world's top 2 scientists, and among them, this is Professor Guo Hai. He is my PhD supervisor, and also we have global organization #1 in Hong Kong, and also we got 4 sim-based research schemes. Among them, 2 of them are related to the environment. And we also have 2 green tech fund and also 1 lentil conservation fund. And also the RGC Collaborative Research Fund, RGC Research Impact Fund. And this RGC CRF fund was founded and the PI is Professor Guo Hai. And also we have the undergraduate program, taught postgraduate program, research postgraduate programs. And we have many outstanding alumni. Also, we have 30 laboratories, 2 workshops, and 1 research center in Shenzhen. And further information can be found in the website and also some social media channels. Okay, so this is the topic title of the seminar, Depicting Photochemical Behavior of Gaseous Secondary Pollutants, mainly focus on ozone and PAN, and in different environments. And also I will introduce some control strategies on ozone pollution control and also PAN pollution control. And the studies are based on the MCM model, the Near-Explicit Chemical Mechanism model. Okay, so this is the contents of the seminar. And I will introduce 6 studies. 4 of them are related to ozone. Okay, and the last 2 studies are about PAN study, and the studies are conducted in different environments like urban, coastal, mountainous, and industrial areas. Okay, so let's first look at the introduction. Okay, we know that both forests and cities can emit VOCs, like biogenic VOCs and anthropogenic VOCs, including aromatics, alkenes, and the precursors, VOC and NOx, are under the sunlight will involve into the ROX cycles, that's the radicals, and it's a central role of secondary formation. And based on the ROX cycle and the NOx cycle, the ozone and PAN and some of the VOCs can produce, that's the secondary gaseous pollutants. And that's the basic mechanism of the photochemical formation. And both ozone and PAN has many side effects. Its impact on human health and on climate change, and also the plants and the crops. And ozone trend worldwide, we can see that the striking increase in Asia, especially in China. And also this figure shows the 6 years trend of ozone over China. We can see there are 3 hotspots of ground level ozone pollution in China. One is North China Plain, and the other is YRD, and also the Pearl River Delta. We live in the Hong Kong, and it's close to the PRD region. And also during the past few years, primary gases or particles pollutants decreased, while ozone still increased. You can see the increase error. And in PRD region, is the increasing rate is 1.1 ppb per year. Okay, and this slide briefly introduced the ozone and radical chemistry. Like I said, both ROX radical cycle and the NOx cycle will produce ozone, and the ozone production has dependence non-nearly with NOx. So you can see it's a curve. Okay, so with the decrease of NOx, then ozone production rate can increase at first, then decrease. That's why some of the control strategy cannot control well the ozone pollution. Okay, and also plus VOCs, we can get this ozone isoplex diagram. Okay, for ozone production. And in addition to the ozone formation, ozone production, also the radicals, we have dependence of OH to NO2 is also the non-linear. Okay, except for the measurements or the classical theory. Okay, that's why the secondary formulation is very complicated. And besides the mechanism, we also notice that the here, this figure shows the different type of environments according to the VOC reactivities and the NOx levels. So we can see in different environment, the ozone precursors are varied. So that's why we need to investigate the environment-specific photochemical behaviors, including the production, destruction, and the secondary formation. Okay. And here shows the research questions. We may mainly focus on 4 environments: the urban and marine, also the mountainous, and 1 industry areas. Okay, the first 3 are basically conducted in the Guangdong province. Okay, here shows the research question. I will further explain them. Okay, so the second part is the methodology, measurements, and the modeling. Okay, so we first conduct the samplings in Hong Kong and adjoining areas in the inland PRD regions. And also we did the sampling at the Nanling Mountains, okay, and also the inland rural, inland urban, and coastal urban sites in the PRD region. And besides, we conducted 10 samplings in 10 typical cities in China. I only introduced our studies in Lanzhou because it's industrial areas. Okay, and the measurement techniques, we used the brief instruments for the trace gases, also PAM, and we used the canister to capture VOCs, and use the DMPH cartridge to capture OVOCs. And we use the GC and HPLC to do the chemical analysis. So here are the 105 species of VOC and OVOCs. And the model, we use the MCM model here, okay, a box model. It has around 16,000 chemical reactions. And we also use the index of agreement, also the relative incremental reactivity, RAR, and also the S+ diagram to do the further data analysis. Okay, so let's look at the results and discussion. The first one is conducted in the urban areas. It's a long-term ozone studies. Okay, from the beginning of 21st century, there were many studies in the PRD regions, but the long-term studies were very few. So this study, ACP studies, maybe the first long-term studies in Hong Kong or maybe in mainland China, is in the South China. Okay, so Professor Wang reported the increasing trend of ozone in this study. And further, Professor Shirley Kun report that the regional transport of ozone increase and neglect the decreased local formation in Hong Kong. So that's why the ozone still increase. Okay, based on these two studies, I conduct the seasonal variation of ozone and its precursors. I found that ozone not only increased in autumn, but also in spring and summer, despite of the decrease of NOx, VOCs, and COs. So the precursors decreased or unchanged, but the ozone still increased. Why? In other seasons. So I did the model simulation to calculate the locally produced ozone. I found that it still increased in spring, summer, but decreased in autumn, which consistent with the shared study. Okay, and based on this, I found that the increasing trend of ozone include two parts. One is regional transport. The other is the locally produced ozone. And in spring, the locally produced springtime ozone increased. That caused the overall increased ozone ambient levels. And in summer, it's due to the increasing sunlight that caused the in situ photochemical reactivity increase, that caused the increased ozone in summer. In summer. And for autumn, the locally produced ozone decreased, but the regional contribution from inland PRD increased. That's why the overall ozone increased. But in winter, no obvious trend was found in winter. We also do the ozone precursor relationship as shown in this figure. We found that ozone VOC reduction strategies would be more effective on ozone control because the RAR of VOC increased. And also we calculate the contribution of VOC to ozone formation. We found that contribution of alkanes to ozone formation still increased. We should be pay attention. Okay. And also after my studies, there were a few further long-term ozone studies. This one is extended year to 2017, and also the Professor Wang Tao, the JRL paper is a 25 years ozone trend, and also Dr. Zhang Yingnan report the increase contribution of biogenic emissions, biogenic VOCs, and also we found some of the ozone levels like OX decreased in recent years. Okay, and except for the long-term studies, we found that most studies are focused on the continental studies in the inland PRD regions or in Hong Kong. A few studies were conducted in the over the South China Sea because the sealant breeze can aggravate the ozone pollution. The sea breeze can send the pollutant back to the continent. So that's why we need to investigate the ozone chemistry in the marine areas. Okay, so we conducted the sampling at Wanshan Island, close to Zhuhai and Hong Kong, and we found the many episodes at Wanshan Island over the South China Sea. 21 episodes, 2 episode events like the shown in the yellow color, and 5 typhoon-induced episodes. Okay, here shows the signal of typhoon. Okay, and further we found that the north winds dominate during the episodes. Okay, and the dirty continental air masses were transported to the marine site. Okay, leading to the elevated level of air pollutants like CO, like NOx, and also VOCs. And also we found the ozone episodes, the hourly level exceeding 100 ppb. Okay, then I need to focus further think what is the ozone photochemistry on episodes. What happened? Then we used a model to find that the ozone formation was VOC limited on episode days, but more sensitive to NOx during the non-ozone episodes. And so from clean days to the episodes, the ozone precursor relationship changed, and also the sum IR values of top 10 VOC species was shown in this figure, and the ozone formation over the South China Sea was mainly caused by a few VOC species, especially for VOCs like formaldehyde, okay, also the acetaldehyde. And control measures should focus on these species to reduce the ozone pollution. And here shows the radical chemistry over the South China Sea. Okay, so on episodes, both OH levels, OH radical levels, and the ROX cyclins increased, and finally the in situ net ozone production increased dramatically. Okay, and we also do the special evolutions of radicals and ozone photochemistries from Hong Kong to the marine site. Dongchong site was close to the Hong Kong airport. Okay, so the distance from Dongchong to Wanshan Island is around 45 kilometers, and we found that during the transportation, the both OH radicals and HO2 radicals increased, and also the ozone production rate increased. Okay, so this model simulation was conducted at 1 day. Is the air masses is from the inland PRD region to the South China Sea. Okay, one tragedy from our sampling days. So from Dongchong side to Wanshan Island. Okay, and furthermore, based on these special evolutions, we conduct the source apportionment to calculate the contributions of continental VOC sources to maritime ozone formation. So we found that the major contribution is from the gasoline evaporation. The gasoline vehicle exhaust, the first one, the red bar, and the second one is the solvent usage, okay, the purple bar. So the emitted contribution of gasoline vehicle exhaust and solvent usage emitted at Dongcheng site at Hong Kong to ozone at the South China Sea were about 55 and 4 ppb respectively. Okay, that's the control policies about the ozone formation over the South China Sea. So this figure is a brief conclusion of the ozone photochemistry over the South China Sea. Okay, we can see the increasing ozone formation, ozone production, and the ROX radical cycling from the continent to the South China Sea. And we found the maritime ozone is produced major contribute by vehicle emission and also solvent usage. Okay, that's the brief conclusions from this second study. Okay, it's back for the urban areas and the maritime areas. We further investigate the secondary pollutant formations in mountainous areas with low NOx emissions but high biogenic VOC emissions. So we have brief studies on ozone levels and the ozone production rate changes among 5 years. So here shows the ozone levels at Nanling background site. We found that here, this red bar is nearly the highest in similar latitude and altitude mountains. Okay, the low latitude and the altitude is around 1,000 to 2,500. Okay, and possibly the ozone levels at Nanling site is the second high in the world. The first high, the highest is a mountain Tai. Okay, and but the mountain Tai is the altitude is higher than, the latitude is higher than Nanling. Okay, so it's close to the North China, and but the levels are close to the mountain Tai. Okay, and we will also see the level is nearly the highest in the Guangdong province. Okay, and we also conduct the diurnal variations and the seasonal variations at Nanling site. We found that the interesting diurnal variations is lower levels during daytime and higher levels during night times because of the Mount Wiley breeze. And we also found the seasonal variation is interesting. It's highest in autumn. Okay, and further, we conduct the 5-year changes of ozone formation at the mountainous background site. Firstly, we found that based on the Blue Book of Ozone Pollution Prevention and Control in China, we found that the observed ozone showed no trend at Nanling site, but the overall background sites, around 16 national background sites, showed an increased ozone levels. Okay, Nanling site showed no obvious, no significant trend. But with our models, we found that the locally ozone production rate are decreased from 2016 to 2020. So that means the no trend was caused by the increased regional transport, a large-scale regional transport of background ozone, because local production at Nanling site decreased. Okay, so this decrease is because the NOx and CO levels decreased, while only the reactivity of VOCs increased, but the overall ozone production rate is decreased. And we further depict the RO2 species, modeled RO2 species. We found that compared to the PRD environments, there are more biogenic related RO2 species, okay? The green one, 3-1 in top 10. But in PRD case, so no biogenic related RO2 species, okay, in top 10 species. And we also depict the contribution of RO2 species to ozone formation. And finally, we calculate the contribution of VOC species to ozone formation at Nanling site. CO contribute half, and also the aspirin contribute. So low contribution of anthropogenic emissions because it's a mountainous migrant site. Okay, and the last one is an industrial area. Okay, we surprisingly found wintertime ozone pollution in Lanzhou. It's an industrial city, and okay, so in the industrial area, the ozone precursors are very high, both high NOx and high VOCs. Okay, compared to other environments. So we firstly summarize the ozone concentration in China during the winter time. We found actually the wintertime ozone pollution are not that scale. Okay, so among them, Lanzhou site has very high ozone levels in winter, and also the frequency of the ozone pollution, ozone episode occurred in Lanzhou are around higher than 5%. So that's why we conducted the wintertime ozone photochemistry studies at Lanzhou site. Okay, and the wintertime ozone pollution is not already reported in the US. Okay, so it's a oil field. Okay, so they found that the wintertime ozone pollution was caused by the OVOCs and also the high snow albedo. Okay, but this previous studies has high levels of alkenes, but at Lanzhou site we found the lower alkenes but the higher alkenes. Okay, at Lanzhou site. So no research for winter ozone pollution with high alkenes. So that's why we need to investigate why the wintertime ozone pollution happened in Lanzhou city. Okay, so here is the sampling site. It's very close to the petrochemical industry. Okay, and here we found in 2018 January we found 4 ozone episodes during the 1 month sampling collections. Also the high level of NOx, okay, and also the high levels of alkenes, okay, higher than 80 ppbs. Usually in other sites, the alkenes levels is around 5 ppbs. Okay. So when we do the model simulation, we found that due to the low solar radiation, the OH radicals should be very low in winter, but alkenes react with ozone it's a dark reaction, can produce the Crigi interminates, it's a radicals. Okay, then the Crigi interminates, I call it CI, can further produce radicals. Okay, both OH, HO2, and also RO2. Then, so the CI accelerate the ROX cycling. Okay, so and further we found the what kind of alkenes that drive this ROX cycling. We found that mainly is propene and butenes. Okay, here, the red one. Okay, and we further compare the reaction rates between alkenes and ozone or OH. We found that ethene and propene has higher reaction rates with alkene and OH radicals. It shows the blue bars. However, the ozone photolysis, ozone reaction with butenes has higher reaction rates. Okay, the red bars. So that's why butene plus ozone can produce more OH radicals. And these OH radicals can help propene to produce ozone because propene tend to react with OH radicals. Okay, so that's so firstly, the butene help to produce the OH radicals. Secondly, the butene, propene react more with the OH radicals. Okay, so finally we found propene and the butene account for around total 70% of ozone formation in winter Lanzhou. Okay, and here shows the depicted map from alkenes to RO2 and finally the ozone formation. Okay. And also, we found that the ozone production caused by butene, here, the dark blue, dark red one are the contribution of butenes are larger than the destruction caused by the butene plus ozone reactions. Okay, finally, it's a higher ozone production rate in Lanzhou site. And for the control strategies in wintertime ozone pollution, we found that the ozone pollution control need to cut 30% peak hour NOx during the at noon. Okay, that's the peak hour, and also can cut 80% propane or butane to mitigate the ozone pollution. However, if we cut the alkenes together, we only cut 25% because the alkenes have the coordination factors. Firstly, butene can produce OH, then propane can further react with OH. So that is a coordination of alkenes. Okay, it's a great contribution. So that's why we need to reduce alkenes together. Okay. Then this slide shows the sub-conclusions. Okay, so in wintertime, the temperature and solar radiation just reduced around 15% ozone formation. Okay, it's a meteorological inhibition. However, the abundant alkenes can promote the CI, Crigi radicals, then produce more OH radicals and produce the propanes to further produce more RO2 radicals, and finally cause the unaccepted ozone episodes during the wintertime in Lanzhou. Okay. Okay, and after we introduced the 4 ozone studies in 4 different environments, we still have 2 PAN studies. One is conducted in the mountainous areas. The other is conducted in the PRD regions. Okay, so firstly, I will briefly introduce the background of the PAN studies. So PAN is a peroxyacetyl nitrate. Okay, it's only some of the VOC can be oxidized from PA. PA radicals is a peroxyacetyl radicals. Okay, then PA radicals can react with NO2 to produce the PAN. Okay, then a high level of PAN can do harm to human health and plant growth. Is similar to ozone, and except the difference with ozone is that the thermal decomposition PAN can do the thermal decompositions to further produce the PA radicals and the NO2. So that means PAN has an influence on atmospheric chemical reactions in clean regions because it can thermal decomposition. So that's why we need to conduct the studies both in high pollutant areas and also the clean areas. Okay, because PAN can be transported to the clean areas and decomposed to PA and NOx to impact the clean environment. So previous studies in urban areas and suburban areas, we found that in totally 30 research papers were collected in mainland China, and only 11 are related to the formation mechanisms. Okay, so but these studies are conducted only in one single site or a short term. So the temporal and spatial distribution of PAN are not clear. And also the quantitative analysis from VOC to OVOC and radicals and then to the PAN formation was not clear based on the 11 papers, 11 mechanical related papers. So that's the 2 research questions. And furthermore, we found only 4 studies was conducted in the mountainous areas, mountain and background areas. Okay, so there are Waliguan, also the Namuchuo and Mountain Tai and the Nanling site. So the photochemical formation of PAN has not been fully elucidated among the mountainous background sites, and also the formation and decomposition of Nanling PAN with higher OH radicals may vary upon the pollutant intrusion. Okay, so that's why we further conduct the PAN studies in both mountainous background site and the urban areas. Okay, so firstly, I will introduce the PAN formation study at Nanling site. Okay, so we conduct samplings in 2018. It's 85 days. Okay, so this study is based on the support of Jinan University. Okay, and we found many episodes. The episodes was PAN level higher than 1 ppb. Okay, so we found 14 episodes. The air masses from north. Okay, and 10 episodes. The air mass from south, from the PRD region. Okay, then we further compare the dynamic variations of PAN and its precursors during the non-episodes and episode north and episode south. We found PAN significantly increased on the episodes. Okay, PAN is here. Okay, the red one, higher than the non-episodes. And also both NOx and VOC increased significantly here, NOx and the VOCs, okay? And also substance, the VOC species level and the diurnal variation vary, okay? So aromatics during the abyssal source was higher, okay? Because aromatics are the typical VOC species in the PRD region. Okay, so we conduct the PAN precursor relationships among non-abyssals and the abyssal NOx and source. We found that, the PAN formation was controlled by both NOx and the VOC. It's a transition zone, okay, from this 3 S-plus diagrams. And the formation of PAN was more sensitive to VOC during the abyssals, okay, during the abyssals. And AVOC, the anthropogenic VOCs, make a greater contribution to the formation of PAN during the abyssals. So we can see here, the AVOC during the abyssals, the blue bar are dramatically higher than the non-abyssals. Okay, that's the changes in PAN precursor relationship from non-abyssals to the abyssals. And further, we use our models to calculate the formation and loss pathways of PAN and PA radicals at non-link site. We found PAN was only generated through the PA plus NO2 reactions, the red one. And the major sink of PAN was thermal decomposition, the blue one. And the net production rate at non-link site, PAN net production rate is positive, okay? So for the formation pathways, we found that the 4 major pathways, okay, shown in the dark box, okay? So they are methyl glyoxyl and acetaldehyde were the main source of PA, okay, shown in the yellow one and in the red one, okay, and followed by the radicals, the pink one, okay, and other VOCs, the green one, okay. So currently, previous studies had only analyzed these 4 pathways, only 4 pathways. So we further conduct depicted the PAN formation mechanism. Okay, so we show this map. It's a contributions of major pathways to PA formation at non-link sites. We found the 4 major pathways in acetaldehyde, mainly from the propane pathways. Okay, the blue one is acetaldehyde. Okay, propane is here. Yes, propane is here. It's the major pathways to produce acetaldehyde, to produce PA radicals. And second one is MGLY. It's a methyl glyoxyl. It's from isoprene and aromatics. Okay, so aromatics, xylene and isoprene can both produce the MGLY. And the third one is radicals. Okay, it's mainly from isoprene. Okay, radicals is black one is mainly from these 2 species is from the isoprene. The last one is other VOCs is mainly from the aromatics. Okay, that's the map. And further, we calculate the contribution of VOCs to PA formation at non-link site. This figure shows the total contribution of VOC species. Okay, once it's shifted to abyssals, the contribution of other alkenes and aromatics clearly increased through the MGLY and other VOC and the radical pathways. As you can see, the anthropogenic VOC species contribute more during the abyssals at non-link site. Okay. Okay, after the PAN study at the mountainous site, we further conduct the spatial temporal variation of PAN chemistry in the PRD regions. Okay, so we have 3 types of sites. One is inland rural. The second is inland urban. The last one is coastal urban size. Okay, so we found the temporal variations of PAN levels were significantly higher in the cold seasons. Okay, you can see the higher levels compared to the warm seasons, low levels. And for the spatial variations, we found the highest PAN levels at the coastal urban site is in Zhuhai. It's more likely to accumulate in coastal areas in the cold season. Okay, and the VOC and the NOx levels are highest at the inland urban sites. Okay, both NOx and the VOCs. So there shows different levels of PAN and its precursors show the different temporal and spatial variations. So it's a little complicated to do the PAN photochemistry. So we conduct the formation and loss pathways of PAN at 3 types of sites in both warm season and cold season. In warm season, we found that the net PAN production rates are all positive. Okay, the black lines. Okay, however, in cold seasons, the net production rates in rural and coastal sites are negative because the higher thermal decomposition rates. Okay, so that means PAN levels, ambient levels can thermal decomposed at these 2 sites in cold seasons. Okay, and we also do the sensitivity test at the coastal sites, at Zhuhai, Meihua sites. We found that this net decomposition of PAN was mainly due to the high levels of PAN at Meihua site and high levels of NOx and not low temperature during the cold seasons. It's around 20 degrees centigrade because it's a relative warm in cold season. That's why PAN decomposed in wintertime at the coastal urban sites. Okay, further, we calculate the contribution of VOCs to PA formations, seeing the 4 major pathways. Okay, so this contribution are basically consistent with the results at mountainous site. And we further calculate the contribution of VOC species we found in warm season. Okay, the green one, isoprene, contribute half. Okay, but in cold season, anthropogenic VOCs dominate the PAN formation. Okay, among them, xylenes, okay, the blue one, also trimethylbenzene, the dark blue one, okay, contribute the most. Also in inland urban site, okay, both warm season and cold season, the butenes, pentenes contribute a lot, okay, the red ones, and also some contribution from propene. Okay, so that's the chemical source of the PAN, okay, in the PRD regions. And at last, we conduct the PAN precursor relationship, and we provide some control strategies in the PRD regions. Okay, so we found that the IR values in inland site, okay, inland rural and inland urban, become VOC limited during the cold season. Okay, become VOC limited, while coastal sites remain unchanged because coastal sites is always the VOC limited. That means control VOCs can reduce PAN formation in VOC limited. However, if in this regime, control NOx can cause increased PAN formation. Okay, and further, we compared the PAN and ozone isoplus diagram. We found that the reduction ratios of VOC and NOx for ozone are also effective in control PAN formation, because PAN has a lower ratios of these precursors. Okay, so that's the control strategies of PAN. And also we use the PMF source apportionment to further calculate the contribution of VOC sources to PAN formation. We found that the biogenic emissions contribute most in warm season, and solvent usage and vehicle exhaust contribute most among the anthropogenic sources. And especially in inland urban areas, combustion sources and gasoline evaporation should be draw attention. Okay. At last, here is a brief conclusions of PAN chemistry in both mountainous and PRD regions. Okay, so we see the net PAN formation rate at Nanling site, the blue one, the red, black one, and no clear change at the inland rural site, and the clear formation in inland urban site, but the net PAN depletion at Zhuhai. Okay, and also we draw a map from VOCs to OVOC, RO2 radicals to PA radicals, and finally to the PAN formation. Okay, so these two PAN studies are published. One is in the EST paper, the other is in Nature NPJ CES paper. Okay, and finally here comes to the conclusions. Okay, so in this seminar we introduced the secondary pollution photochemistry in 4 environments. Okay, the urban rural areas, we investigate the long-term ozone precursor relationship. Okay, and also the PAN chemical special temporal variations of PAN chemistry. Okay, also conduct the control policies of PAN pollution. And secondly, the coastal marine areas, we conduct the ozone photochemistry over the South China Sea. Okay. And the third one is the mountainous areas. We investigate the ozone levels and the 5 years ozone production rate changes at Nanling site, also the PAN formation at Nanling site. And the last environment area is an industry area. We introduced interesting wintertime ozone pollution in Lanzhou site, okay, caused by the alkenes, okay, and also the control policies of high alkenes environment, okay, and also have some possible research extensions in future, maybe more species, especially the OVOC species, okay, and also we maybe can establish an RO2 radical database in different environments, and also we can add more new mechanisms and use more models to do the secondary pollutants mechanisms. Okay, and in the future, maybe our research groups will do more studies in the coastal urban mountainous atmosphere of southern China. Maybe the transportation process during the transport, okay, chemical process. Okay, that's all. Thank you.
Thank you, Dr. Wang. We'll now proceed to the Q&A session. Please feel free to leave a message to the chat room if you have any question regarding the webinar.
the more informations of these seminar can be found in our published papers. And if you want to get the papers, you can also email me to get these papers.
So if there are no questions, we'll go to the closing. Thank you, Dr. Wang, as the speaker of today's webinar. We have prepared carbon credit certificates for you as a token of thanks. I'm sure all of us have learned a lot today and hope you have enjoyed the webinar. The digital attendance certificates will be sent to your email in 4 weeks. Once again, thank you very much for joining the webinar, and we wish you a good evening. See you all again in the future events. Goodbye.
Okay, thank you. Goodbye.